In this lesson, we will be looking at molecular formulas. Molecular formulas, quite simply, are just a multiple of an empirical formula. Now, as we talk about molecular formulas, we are only dealing with covalent compounds. So there are not going to be any ionic compounds involved in this, no calcium, no copper, no sodium compounds. Quite simply, the molecular formula, it's an empirical formula in which some multiple of that is what we are trying to determine. To give you an simple example, we could have these various chemicals, C4H6, C6H9, C20H30. And for all of them, they are the multiple of C2H3. Every single one of those has the multiple of C2, it has an empirical formula of C2H3. So what are we ultimately trying to do? We're trying to ultimately realize what is the variable? What is that multiple? And we can see we have, it's the empirical formula times 2, times 3, or times 10. And that's what our goal is as we go through to solve these problems. Our steps are quite simple. Number one, we may need to find the empirical formula. Now, if it's given to us, then that's convenient, and we're able to move on to the next part of the problem. If not, then we just need to calculate the empirical formula. After we've determined the empirical formula, we're going to compare the molecular mass of the empirical formula and the molecular formula. Now, to accomplish this, we have to be given the molecular formula. Okay? If we're not given the molar mass of that molecular formula, then we don't have enough information to solve this problem. Once we have that, we can now determine our value of n. Once we know our value of n, we now know what the molecular formula is in terms of a multiple of the empirical. Quite simply, it could be a problem like this. We have some molecular formula, CXHY, in which they tell us the molar mass is 58.086, and they tell us that the chemical's empirical formula is C2H3. And we are obviously trying to identify what the values for X and Y are. So we're going to compare the molar mass of the molecular formula to the empirical formula. They've given us the empirical, and we just have to then quickly look up what the molar mass is for that empirical formula, and we get 27.041. So we can see the relationship here of 54 to 27 is a 2-to-1 ratio. So our molecular formula is twice as large as our empirical formula's molar mass. Therefore, the molecular formula, okay, if n equals 2, then we have 2 times that empirical formula, and we have a final molecular formula for this chemical of C4H6. If I do a sample problem here, the one in the book on page 248 that involves phosphorus and oxygen, you're able to follow through in that example. The hardest part about these problems is just being able to pull out the information that is necessary to do the calculation. So if we read the sample problem on page 248, the empirical formula of a compound of phosphorus and oxygen was found to be P2O5. So we know the empirical formula is P2O5. Experimentation shows that the molar mass of this unknown compound is 283.89. What is the compound's molecular formula? So again, we're trying to find out the value for PXOY. Quite simply, we just compare the molar masses of the two. We have the molar mass of the molecular. We need to know the molar mass of the empirical. And as you can see, they work through this in the book, 141.94. So if we compare 141.94 to 283, we see it's a multiple of 2. Therefore, the formula as they work out in that problem becomes P4O10. Okay. And again, you're able to kind of look through those steps and follow through what they've done in the book there on page 249. One other example that we'll do here is if we look on practice problem number 1 there at the bottom of 249, determine the molecular formula of the compound with an empirical formula of CH and a formula mass of 78.110. So if we read that practice problem, number 1, this is basically what we have. We know the empirical formula is C1H1. We're trying to figure out the value for the molecular formula, which is CXHY. And we know from the question that they give us the molecular formula to be 78.110. If we add up the molar mass for one carbon and one hydrogen, again, depending on how many decimals we use, we can simply just leave it as 13.01. Trying to find the relationship here. What does N equal? Some people might be able to see that 13 and 78 is a 1 to 6 ratio, so N equals 6. If you do not see that right away, then we simply divide by the smallest. Dividing the smallest by itself gives us 1. Dividing by the smallest gives us 6. Therefore, our molecular formula is 6 times the empirical, so C6H6. And that concludes the tutorial on molecular formulas.